This video is on recursion, but in order to do recursion properly, we have to start out by defining sequences. So a sequence is really just a function from the natural numbers into some set. Usually we're going to be dealing with the real numbers. But practically speaking, we just tell you, like in this case right here, how to write out what the terms of the sequence are. So if we let an be given by 3 times n plus 1, well, to get the terms of the sequence, it's exactly what it looks like. So for the first term, a1, you plug a 1 in for n. For the second term, you plug a 2 in for n. For the third term, for the a3 term, for the a4 term, so on and so forth. And then you just do the calculations. So 3 times 1 plus 1 gives you 4. 3 times 2 plus 1 gives you 7, and so on and so forth. So that is what a sequence is. Now we're focusing on sequences that are given recursively. So let's talk about what that means for a sequence to be given recursively. And I'm going to jump down to 10.2. A recursive sequence means we use previous terms of the sequence to define the sequence. So in this example, an is defined as an minus 1 plus n times an minus 2 plus 1 for n bigger than 1. But then I need to tell you what the earlier terms are. And also notice in this one that this sequence started at 0. Sequences don't always have to start at 1. They can start at 0. Sometimes you will start a sequence at 2 or at 3, but usually we'll start them at 0 or 1. So make sure you always pay attention to that. Make sure you pay attention to where your sequence starts. So I know this example is given right here. At the end of this video, I've worked some of the problems from the handouts, but I do want to go through this one in detail just so you can see how it works, live. So using this definition, a0 equals a n minus 1 plus n times a n minus 2. Excuse me, that's made a mistake right there. That's the general definition. That is a n. And then we're told that a 0 is 1, a 1 is 2. Well, then what would a2 be? Well, a2 would be, well, think about how the sequence is defined. an is defined as the one right before it, an minus 1, plus n times the one that came 2 before it. So a2 would be a1, the one that comes right before it, plus my n term is 2 because that's where I'm at. So this would be 2 times the one that came twice before it. So this would be a0. So that's going to give us 2 plus 2 times 1, which is just 5. And you can see that right there. I'll do a3. a3 would be a2 plus 3, because that's the term we're on, times a1. So a2 was 5, plus 3 times a1 was 2. That's going to give us, whoops, I left off a 1. I left off adding 1 to these. There's a plus 1 on the end. So plus 1 to actually make that 5. And plus 1 right here. So this would be 5 plus 6 plus 1, which would give us 12. And because I made a mistake on that, I'm going to go ahead and work out a4 as well. a4 would be a3 plus 4, because I'm on the fourth term, times a2 plus 1. That would be a3 was 12 plus 4 times a2, which was 5 plus 1 more. And that's going to give us 20 plus 12 plus 1. That'll give us 33. So that's how you write out the terms of the sequence when you have a recursively given sequence. Now, the most famous recursive sequence is probably this one. It's called the Fibonacci sequence. And it's defined like this. You define the first term of it as 1, the second term as 1, And then anything above that is the sum of the previous two. So watch this. And I'm going to write it with A's just so you can get used to seeing it different ways. So A1 is 1, A2 is 1, and then AN is going to be AN minus 1 plus AN minus 2. And this is the Fibonacci sequence. So A1 is 1, A2 is 1, A3 would be A2 plus A1, which is just 1 plus 1, which is 2. A4 is A3 plus A2, but that's going to be 2 plus 1, which is 3. A5 would be A4 plus A3, which is going to be 3 plus 2, which is, oops, I got ahead of myself. 3 plus 2, which is 5, and so on and so forth. So that's how you would do the Fibonacci sequence. Here's another example of a recursive sequence. Find the first 6 terms of this sequence. CK is 1 over k squared. And this can be given by the function f of x equals 1 over x squared. So when you write it like this with this function term of an x, you're thinking of using real numbers. So you would get a continuous function. But when you do it like this, when we only plug in 1, 2, 3, 4, we're going to get discrete values. And here's kind of the comparison of those two graphs. This is when you plug in a 1, you're going to get 1. When you plug in a 2, here's 2 on the x-axis, you're going to get 1/4. When you plug in a 3 on the x-axis, you're going to get 1/3. And so this is what the terms of the sequence do. They go down this way. And then beside of it, we have graphed for all values of x between greater than 0 and up to 5. This is the graph of the function. Notice that these discrete points appear on this graph. So here is, if we plug in a 1, we would get this value right here, 1. If you plug in a 2, you're going to get this, which is about at 1/2. Plug in a 3, you're going to get about 1/9, and so on and so forth. So you can kind of compare those graphs. When you're comparing these, you would only want to compare like this window right here, right? The one on the left is kind of that window kind of magnified up. So that's how they kind of fit together. And this is the way that you can compare sequences with functions. Okay. Now, one thing we like to do when we have recursive sequences is find what's called a closed formula for the sequence. And that's when you find an explicit formula that doesn't refer back to itself. So starting out, we want to be able to check and see if something is a solution or is a closed formula for the sequence. So let's look at AN, where AN is given by 2 to the n, okay? And we want to decide whether or not this is a solution to this recurrence relation. AN equals 2 times AN minus 1 minus AN minus 2 for n greater than or equal to 2. Well, just plug in some values and see what happens. If you plug in values to the equation, we're going to get A0 equals 2 to the 0, which is 1. A1 is 2 to the 1, which is 2. A2 would be 4. And so that's enough to see that that recurrence relation is not a solution. Because if we use the recurrence relation and check it for A2, this is what we're going to get. We get that A2 equals 3. So that's not a solution. It's not a closed formula for the recurrence relation. And at the end of the video, again, I have some worked examples, and there'll be some linked in the notes as well. Now, we can solve a recurrence relation using a process called iteration. So suppose we want to solve this. AN equals AN minus 1 plus 3, starting out where AN equals 2. So what we want to do when we solve this, we write it down iteratively. So A2 is A1 plus 3. That's from the recurrence relation. But what's A1? A1 is 2, so we write that as 2 plus 3. So keep that 2 plus 3 written like that. A 3 is going to be a 2 plus 3, but we know what A2 is. We have a way to write A2. It's 2 plus 3. So A2 plus 3 will become 2 plus 3 plus 3, and we can simplify that as 2 plus 3 times 2. We're grouping those 3's together. The next term, A4, is A3 plus 3, but we have a way to write A3 right here. So A3 is 2 plus 2 times 3, then we're adding another 3 to it, and now look what we have. This is 2 plus 3 times 3. So in general, what we're going to get for AN, that's going to be AN minus 1 plus 3, but this turns into 2 plus 3 times N minus 2. That N minus 2, notice what happens with, right here and then right here in these two terms and in this term. And then we have the extra 3 added. So in general, this is going to turn into 2 plus 3 times N minus 1. And this is the closed form solution to the recurrence relation. AN is going to be 2 plus 3 times N minus 1. Now, in general, when we're talking about recursively defined functions, they have two parts. They have something called the basis step, which gives you the value of the function at 0 or 1. Sometimes we'll start at 1. And then we have what's called the recursive step, which is the general rule. Okay? And we've seen that in those previous sequence examples. But let's look at the Fibonacci sequence again. Okay? This time I'm going to write it as a function f of n, where I'm going to start at 0, f of 0 is 0, and f of 1 is 1. And then the function will be given like this. So what is the basis step and what is the recursive step? Well, here is how I'm telling you to start. This is how we start. So this is the basis step. And then I have the general formula, which is the recursive step. Okay. And then things work the way that they did previously. All right. Moving on to recursive algorithms. Now, a recursive algorithm is an algorithm that calls itself. Okay. A recursive algorithm is one that calls itself to do its calculations. So let's look at an example of doing this with factorial. Okay. Remember that 5 factorial is 5 times 4 times 3 times 2 times 1. But look at another way that we can write that. We don't have to write it as 5 times 4 times 3 times 2 times 1. We can notice that these terms right here are equal to 4 factorial. So that means we can write 5 factorial as 5 multiplied by 4 factorial. And recursively, we could write a function for the factorial as we could say f of n is going to be equal to n times, or sorry, let me do that a little bit differently. We can write it like this. We could say n factorial is going to be n times n minus 1 factorial. That's our recursive step, and the basis step would be 0 factorial equals 1. That tells us where to get started. And so then we could, we have to do all the previous ones, but we could calculate any factorial we wanted. So for example, if I want to do 4 factorial this way, this would be 4 times 3 factorial, but that's going to be 4 times 3 times 2 factorial, because remember, factorial is defined recursively now. This is 4 times 3 times 2 times 1 factorial, but that's 4 times 3 times 2 times 1 times 0 factorial. And now we're at the basis step. So this would be 4 times 3 times 2 times 1, which would give us 24. So that's writing factorial recursively. here's how we could do that in Python, okay? Define recursive factorial. That's what the R factorial means. So we start out by defining z to be 1, and if n is greater than 1, we define z to be n times R factorial. Notice, and this people don't like this when they first see it, but I'm calling the function inside where I'm defining the function. But that's what makes it recursive, okay? And then I'll just return z. So this is my basis step. This is getting me started. And then for anything bigger than 1, I'll just call the function. Now, it takes a lot of steps to do this. And if you try to do this for a large number, the Python tutor in particular is just going to stop. But let's just walk through this for 5. Okay. So there's my function defined, recursive factorial, R factorial. So I'm going to call it where n equals 5. So z is 1. And now look, I'm calling the function itself. But now it's calling it for n equals 4 because I have this n minus 1 inside there. So the next step, z is 1 now because it checks that again, or it does that definition again. And now I call it for 3, R factorial of 3. Do it again for 2. Do it again for 1. Whoops. So you can notice that it keeps moving down there. And z is starting to change now because z is going to be n times recursive factorial times n minus 1. It's hard to show this on the screen because I don't have a lot of room, but what I would encourage you to do is to go ahead and go to Edit in Python Tutor and walk through this yourself. So if we walk all the way to the end, we're going to get that the return value is 120. And then it's going to say n factorial is 120. So this is one of those times where I encourage you to walk through this yourself and try it with a couple different examples. I'm going to also encourage you to look at this with a recursive definition of the power function, okay? The way this one works is, we know that 5 to the 4th is just 5 times 5 times 5 times 5, but another way to write that would be 5 times 5 cubed. So a recursive definition of a power function would be start out by saying b to the 0 is 1, and then b to the n is going to be b times b to the n minus 1. So we're giving the power function recursively. You can do that with arithmetic sequences. Here is Python Tutor giving the Fibonacci sequence recursively. This is another one that I'm going to encourage you to go ahead and try to work through yourself. But I'm going to move on to looking at the notes now. Okay. Again, the notes are just summarizing what's in the book, but in particular, look at these examples and then watch these videos because these are some other examples of writing a recurrence relation, checking to see if something's a solution. This one I think you're going to find really helpful, solving a recurrence relation. And then we have some practice problems. The second set of recursion notes is all about algorithms. Here's the code for the recursive factorial. Here's the code for the recursive power function. Here's a video example of a recursive algorithm in Python. And I want to encourage you to spend a lot of time looking at the merge sort algorithm. Now we're going to get into sorting algorithms and a little bit later, but I want you to spend some time looking at merge sort. Here's a video that traces through merge sort that'll help you understand it, and there's a video on the merge sort dance. I very highly encourage you to watch those videos to understand how merge sort works. And then we have some more practice problems, which I'm going to work out some of those practice problems right now. Okay, so for this first example, we're just going to, we just want to write out the first 5 terms of the sequence. So I'm just going to do the first one, part A, because the other ones are very, very similar. So I'm just going to rewrite this so we can see what we're talking about. So the sequence is defined as A sub n is equal to 6 times A sub n minus 1, and then A0 is defined as 2. So this is our starting point. This is like our basis term. Okay, so A0 is just defined as 2. A1 is, now we go back and we look at how the sequence is defined. Okay, so it's 6 times the one previous. So A1 would be 6 multiplied by the one before it. That's A0. But that's going to be 6 times 2 because that's what A0 was. So we get 12. A2 is going to be 6 times the one before it, which is going to be 6 times 12. So we get 72. A3 is going to be 6 times the one before it. That's 6 times 72, which gives us 432. So those are the first four terms of the sequence. And then because I'll start out at 0, this is the first one, the second one, the third one, the fourth one. And then the fifth one would be A4. And the reason I pointed that out is it can get a little bit confusing because I'm asking for the first 4 terms. But since I started at 0, asked for the first 5 terms, but since I started at 0, the 5th term will be A4. So just keep that in mind whenever you're asked for certain terms. So then A4 is going to be 6 times A3, which will be 6 times 432, and that is 2,592. So that's the first 5 terms of that sequence, and you do all the other ones similarly. The only thing I would add is that, when you're doing these last couple, here A0, A1, and A2 are given to you, so you'll have 3 parts of your basis term. So you'll start with A3, which will be given in terms of these. So just watch out for that. So for the second problem, we want to show that each one of these sequences is a solution for the given recurrence relation. So let's just do C. All right. So on this right-hand side, I'm just going to write down the sequence. So AN equals -4 to the n. So A0 would be -4 to the 0, which is 1. A1 would be -4 to the first, which is -4. A2 would be -4 squared, which will give us 16. A3 would be -4 cubed, which would be -64. A4 would be -4 to the fourth, which is 256. And that's probably enough to get an idea of what's happening. So on this right-hand side, I'm going to write down the recurrence relation. So AN is going to be -3 AN minus 1 plus 4 AN minus 2. And since to do this, I need to know at least 2 terms, we'll start out by defining A0 to be 1 and A1 to be -4. And then for A2, we can start looking at the recurrence relation. So this would be -3 times A1 plus 4 times A0, which will give us -3 times -4 plus 4 times 1. But that's 12 plus 4, which is just 16. Okay, so that one matches up. A3 will be -3 times A2 plus 4 times A1, which is -3 times 16 plus 4 times -4. That's -48 minus 16, which is -64. That one works. And then we'll check A4. This is -3 times A3 plus 4 times A2, which will give us -3 times -64 plus 4 times 16. That's going to give us -3 times -64 is 192. Plus 64 is going to give us 256. So what we get is that the A0 terms match up by definition, but these other terms also match up. So that's an indication that these sequences are solutions to the recurrence relations, which is enough for what we're doing here. So that's how I would like you to approach these problems. Now, moving on to the next one. Let's find a solution to each of these recurrence relations using the given initial conditions. So I'm just going to do, I think, this first one. Okay, so here's how you go about doing this. And again, there are examples in the book and there are examples linked in the notes. But if I'm going to show that an equals negative an minus 1, where a0 is 5, I want to find a solution. That is, I want to be able to write the recurrence relation as a sequence so that it doesn't refer back to itself. So let's just look at some of the terms. A0 is equal to 5, that's by definition. So A1 is equal to, using the recurrence relation, this is going to be negative A0, but that's just negative 5. A2 is going to be negative A1, but A1 is defined as negative A0, so that's negative A0. So that's just going to give me A0, which is 5. A3 is negative A2, but A2 is just A0. So this is negative A0, so I get negative 5. A4, well, that's just going to be negative A3, but we know that A3 is negative A0 from the previous step. So this is negative A0, which is just going to give me a positive 5. So look what happens. I'm just alternating back and forth from 5 to negative 5, from 5 to negative 5, from 5 to negative 5. Let's do one more. This is going to be negative, this is going to be negative A4, but A4 is just A0. So this is negative A0, so A5 again. So that tells us that we can write AN, well, it's always either plus or minus 5. So I'm going to be multiplying something by 5. And to get that plus or minus, I'll multiply it by negative 1. Now notice, whenever we have an even power, it's positive 5. When we have an odd power, it's negative 5. So if I just take negative 1 and raise it to the n, that works out the way I want it to. If n is 0, I just get 5. If a is 1, if n is 1, I'll get negative 5, and so on and so forth. So that's the that's writing this as a sequence. An is negative 1 to the n times 5 for n greater than or equal to 0. And so that's how you'll go about doing these problems. You'll write out the terms, and then you'll use what is defined previously to write it out just as a sequence. And let's look at the next problem. So in this one, we're kind of doing the opposite. We are starting out with a sequence, and we want to write it recursively. So again, I'm just going to do the first one. So an is defined as 6 times n. So let's write out some of the terms. And notice we are starting at 1 here. So a1 is just equal to 6 times 1, which is 6. a2 is 6 times 2, which is 12. A3 is 6 times 3, which is 18. A4 is 6 times 4, which is 24, and so on and so forth. So look at the terms of the sequence. And what are we doing to get to the next one? Well, to get from 6 to 12, one way to think about it is that we multiply by 2. But if I multiply 12 by 2, I get 24, which isn't my next term. So I'm not multiplying by 2 if I want to write this out recursively. Another way to get from 6 to 12 is to add 6. 6 plus 6 gives me 12. 12 plus 6 will give me 18. 18 plus 6 will give me 24. So that must be what it is. So we can write this recursively in the following way. We'll say that an is going to be an minus 1 plus 6, where the first term is just defined to be 6. So a1 is 6, A2 is A1 plus 6, which is 6 plus 6. A3 is A2 plus 6, but that's just 12 plus 6, which is 18. A4 is A3 plus 6, but that's 18 plus 6, which is 24. And I think you see it right there. Okay, so that's how you'll do that one. Write out the terms of the sequence and then figure out how to give the same thing recursively. Okay, this last example, we want to give a recursive algorithm for finding the sum of squares of the first n positive integers. Now remember, a recursive algorithm calls itself. That's what makes it recursive, okay? So here's a way to think about this. Let's suppose we had a function, for n, a positive integer. Suppose we had a function I'm going to call Sn that did this. It did 1 squared plus 2 squared plus 3 squared plus ... plus n squared. Now, there actually is a closed form of this, which I'm not going to get into, but it's a really interesting thing to think about and to kind of investigate. But we want to do this recursively. And to do this recursively, notice that another way to write S of n would be like this. This is equal to 1 squared plus 2 squared plus 3 squared plus ... plus n minus 1 squared plus n squared. But I can write this as S of n minus 1 plus n squared. So notice that when I write the function this way, that when I sum all of this up and I say Sn is equal to Sn minus 1 plus n squared, I am calling the function to define the function. So I'm doing this recursively. So now how could we write this as an algorithm? Well, I'm going to use Python syntax because that's what we do in this class. So I could define a function. I'm going to call it sum of squares, and it's going to take an n, and so ultimately what this is going to do is it's going to return, well, it's going to return itself, sum of squares of n minus 1, and then add to that n times n. So that's what the function is going to do. But we need to be careful because if n is 0, I'm not going to be able to count down. Sorry, if n is 1, I'm not going to be able to count down. So we'll add one more thing in here. We'll say if, I need some more space. So let me write it like this. Let me insert some space real quick right here. And I'll say if n is 1, then I want to return 1. All right. And then, but if n is going to be bigger than 1, then it will run the next return statement, and it'll call itself, and it'll recursively give me what the sum of squares is. So I encourage you to try this in Python Tutor or whatever IDE you use to check it out and make sure that it works.